Hey everyone, so today we'll actually be looking at deeper neural networks using residual connections. I know I mentioned in the last video that we'd be doing recurrent neural networks and sequence modeling, but I think this is actually pretty important and I want us to learn to implement a actually used state-of-the-art neural network like a ResNet rather than the AlexNet that we looked at last time. So today we're going to be looking at that. We're going to get a better intuition about backpropagation. I know we did this in the very first video, but there are some limitations to backpropagation, and that's what we'll be exploring today. And we're going to see how residual connections is a solution that's used, and residual connections are actually used across the board in basically every neural network out there today. Because it's so important, it actually allows us to train super deep neural networks. And you can think about transformers and other models, and they're all using it in some way or the other. So we do need to talk about this. It's super important. So we're going to first start with the math of residual connections. Basically, what is it? Why do they allow us to train deeper neural networks? What's the problem with backpropagation? Why can't we train deep neural networks? And once we get that done, then we're going to implement ResNet, which isn't a very hard architecture to implement. It's more annoying and finicky than difficult. So you'll kind of see that there's a couple exceptions we're going to handle, and we're going to get through this just fine, and you will understand residual connections, which will show up all the time in all sorts of architectures you're going to look at in the future. So let's go ahead and set the stage for why we need residual connections. So we're doing today residual connections. All right. So I am going to do the most bare bones neural network possible just to kind of explain what's happening. And we're going to do it once with residual connections and once without residual connections, and actually write all the derivatives out of what they look like and see what residual connections are adding that without having them, you'd have a problem. So what we're going to do is a very simple 3-layer neural network. So let me scroll down just a little bit. There we go. So what we're going to do is we're going to have some x, and it's going to go into 3 layers. So let's call this the first layer. Let's make this the second layer. Let's make this the third layer. And what we're going to do, and just to again make this simple, we're going to be multiplying by a single number, so a single weight in each one of these, so nothing crazy. So you don't have to deal with matrices and the complexities that come with that. And there will be no biases, again, just to make this as simple as possible. So we're going to call this W1. That's the weight inside here. The second one W2. The third one W3. And these are going to, it's going to be just a regular forward propagation. And let's call this intermediate A, intermediate B, and the output C. C is then going to go to compute some loss, right? It doesn't really matter what the loss is. We're going to do the mean squared error loss, or just squared error loss, just to keep things simple. So let's just write out exactly what this is. So we've seen before that neural networks are really just a nested chain of functions. Also notice that I did not include any activation functions or anything. It wouldn't change anything. It just make the writing more complicated. So this is just to keep it as simple as possible. So let's write out a little bit of what this looks like. So A is just W1 times X, right? So W1 times X. B is going to be W2 times A, and then C is going to be W3 times B. And you can imagine that this A here, this would go right there, and then all of this would go right here. And we can write this out as a single function by actually nesting them together. So we can write C is equal to W3B. So W3B is just W3 times W2A, and W2A, A is just W1X. So we can just write this as W3 times W2 times W1X, right? Very, very simple neural network. We're just multiplying X by some coefficients. Again, there's no activations or anything. Not that it would change anything. It would just make the writing more annoying. So we're going to leave it like this. And we need to pick a loss function. So like I said, our loss function can be, let's say, C minus C hat squared. let's pretend, so this C is our output of the neural network, what we're predicting, and C hat, let's just pretend this is the truth, right? Ground truth, because we need to compare our data to some ground truth. Now, as you can imagine, when we take this derivative, like dl dc in the future, it's going to be 2 times c minus c bar. Just so we don't have to keep writing that 2 over and over again, I'm just going to stick a half in the front, because minimizing something is the same as minimizing half of that thing. So adding a constant doesn't actually affect our optimization. It just simplifies the writing a little bit. So what we know in neural networks is we need to take the derivative of our loss function with respect to all the parameters in our model. And this is for both weights and biases. Normally weights are different matrices and the biases are either a number or a vector. We don't have any biases in here, just to keep it as simple as possible. And the weights are just single numbers, again, just to keep it as simple as possible, because the principle of this is identical regardless of what we're doing. So let's go ahead and do that. So what we need to do is to take the derivative of our loss, L, with respect to W3, W2, and W1, right? The parameters that we want to update in our model. So we need to take the derivative to actually do gradient descent. So let's go ahead and do the first one. So dl dw3 is the first one, and we're starting with w3 because it's at the end of the model. It's the outermost parameter, and we'll obviously have to do chain rule to work our way in. So we're going to start on the outermost and work our way in. So dl dw3, well, the first we need to get, so we need to go from L to C and then C to W3. So we need to do dl dc, the derivative of the loss with respect to C. And then we need to do dc dw3. And notice that these two things are equivalent, right? Because dc and dc cancel, and you're left with dl dw3. So these are equivalent. So let's go ahead and evaluate it. dl dc, what's the derivative of the loss with respect to c? Well, just like chain rule, we're going to do the 2 comes out in front. So it's going to be 2 times 1/2 c minus c bar. And the reason we did this is just so we could cancel those 2's. So we can cancel these 2's and not write them. And then we need to do dc dw3. What's the derivative of c with respect to w3? And you should know from calculus, if you have y equals ax, dy dx is just a, right? The constant. So if we're doing dc dw3, we'll just be left with b. So this will be b. And so we can rewrite this as c minus c bar times b. And that's our first derivative. So nothing crazy just yet. Let's do the next one. dl dw2, right? So let's take this derivative. So we need to work our way into here. We need to work our way to w2, which means we need to go from c to b, because w2 exists inside b. We need to go from c to b and then b to w2. So we can rewrite this as, let's get rid of these so it stays clean. This is going to be equal to, again, dl dc, because we need to go from L to C. Then to get to W2, W2 exists inside B, so we need to see how does B change with respect to C. So we need to do dc db, and then we can do db dw2. Again, notice that both of these expressions are equivalent because dc and dc cancel, db and db cancel. You're left with dl dw2. So that's, again, just chain rule. And so we can then go ahead and evaluate this. Notice one thing, this dl dc and this dl dc are the same, right? So we can use that information. So any efficient implementation of backpropagation will kind of reuse stuff that has already been computed in one of the earlier steps. So dl dc, like we saw before, is just c minus c bar. So it's going to be c minus c bar. dc db, well, let's see. So dc db would just be w3. So there we go, w3. And then db dw2, db dw2 is just a, for the same reason we had this b earlier, right? So there we go. That's our derivative with respect to W2. Let's go ahead and do the last one. We're going to do dl dw1. And again, for the exact same reason as before, let's scroll up a little bit. We need to go from L to C, C to B, B to A, and then A to W1. Right? That's the path we have to take. So let's go ahead and write that out. This is again going to be the equivalent of dl dc, dc db, db da, and then da dw1. So that's our, again, chain rule. And we can go ahead and rewrite this as C minus C bar, because we know what, actually we know all of this. So like I said, any efficient implementation will just copy over information we know. So these two things are the same, so we can reuse that information. So we know C minus C bar, and then W3 get copied over. And then dB dA, we can quickly take a look at that. dB dA will be W2, and then dA dW1 will just be X. So this will be W2 X. And this is our chain rule. And you could imagine that if we have a deeper neural network with more layers, this chain will continue. And so here's the problem that I want to this is the problem I want to propose for backpropagation and why we have a problem in deep neural networks. Let's pretend, right? So let's just pretend we create a very, let's say DL, the letters I'm about to use right now have nothing to do with the problem above. This is just an example. We're going to do DL, DA, DA, DB, DB, DC, dot, 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 and we'll end up with like DY, DZ, or something like that, right? We're trying to find DL, DZ. I don't know, something like that. So let's say there is 1,000 things being multiplied, right? So we have 1,000 things in our chain rule because we have let's say 1,000 layers in our neural network or something like that. What happens, right? Problem 1. What happens if the derivatives are small, right? What happens if you multiply a ton of small numbers together? You'll have something known as gradient underflow. What this means is, let's say the first derivative was 0.001, and then the second one was 0.001, 0.001. I'm just making up numbers. But you multiply a bunch of these things together, you're going to get a number that's effectively 0. Which means when we go to update our model, like we're trying to update early parts of the model. Because remember, we have 2 steps in neural networks. Step 1 is forward propagation, going this way. Forward propagation is no problem at all. But then we have backward propagation, which leverages chain rule, right? Leverages chain rule to actually do the update step. But if for me to get to the beginning of the model and I have to chain through all of these different layers of the model and multiply all those gradients together, because chain rule is a multiplication operation, then I have a bit of a problem. Because as I stack these chain rule derivatives together, if all these derivatives are really, really small, then I'm going to end up with a number that's effectively 0. And so when I go to update my weight, like if I want to update, in this case, W1, right? I want to update W1. So in gradient descent, right, our update step is W1 will become W1 minus the gradient of W1, right? And the gradient with respect to the loss times some learning rate, right? Some alpha. So that's our typical update step for gradient descent. Well, if this is basically 0, then W1 will just update to W1 minus basically 0, which will stay as W1. So we actually cannot update W1 with respect to the gradient, or with respect to the loss, because the gradient information always comes out to be 0. So this obviously does not work. Problem number 2. What happens if derivatives are large, right? Big derivatives. So let's say the derivatives were like 10 times 10 times 10 times ... We'll effectively end up with something that's infinity, right? Beyond the precision. And a lot of this also comes down to floating point precision, like how much floating point precision the computer actually allots us to do these operations. But if you multiply 1,000 tens together, that's a huge derivative. And if when we again go to do our update step, like W1 is W1 minus what's effectively infinity, this will be an extremely unstable training regime, right? W1 will just be all over the place, no matter how small of an alpha you pick for your learning rate. So that's the problem, right? We have gradient overflows, gradient underflows, and this is just a typical problem for deep neural networks. We haven't really dealt with this yet in the case of our AlexNet or our kind of simple MNIST examples we've did, because those were not very deep neural networks, right? There was only a handful of layers. AlexNet only had maybe 10 or 15 layers or something like that, and our MNIST model only had 5 or 6 layers. But what if we want 50 layers, 100 layers, 1,000 layers, or even more complicated models with more things going on, like some of the large language models that we see today? So we have a problem, right? And what the ResNet paper proposed is a solution to this using something known as a residual connection. So a residual connection, let's kind of just pull up the figure real quick before we do the derivation. Here we go. A residual connection looks like this. And you can go through this derivation as well, but I'm about to do one more detailed than I have in this Jupyter notebook, so you can ignore it. We'll come back to this. This is the residual connection. And there's different types of residual connections, but the most typical one is the additive one, where you can imagine, let's pretend this residual connection is not there right now. You can imagine when we do chain rule, when we're doing backpropagation, we have to propagate through the weight layers, right? We have to backpropagate through these weight layers. And as you stack these weight layers together, you have to multiply more and more things, which is the problem, right? The whole problem is we're multiplying too many things together. So when we're doing backpropagation, you have to multiply even more things together to get back to the end. The identity, this additive identity here, provides backpropagation a different pathway to send those gradients back. So now for gradients to flow back, it has to go both through these layers, but it can also circumvent these layers, go around them. And why this works mathematically is basically what I want to show you. And so let's go ahead and do that. I hope this made sense. So again, 2 problems, gradient overflows, underflows. Overflow is actually easier to deal with because we can perform something known as gradient clipping to make sure problems like this don't happen. And maybe you'll have a couple of iterations of gradient overflows, but it seems to fix itself as it begins to train. Underflow, there's actually nothing we can do about this, right? If all the gradients are just going to 0, then there's really nothing we can do to fix that. So because that information is lost. So let's go ahead and do another example. So we're going to do the exact same model that we just did, but now we're going to add in some of those residual connections and see how it affects the derivation. So what we're going to do is, again, we're going to have our first layer right here, W1, second layer here, W2, third layer here with a weight W3. Let's write that 3 a little better. And just like before, we're going to have A, we're going to have B, and we're going to have C. So this is exactly what we had, and this is going to go to some same mean squared error loss as before. But now what I want to do is add in some additional residual connections. So what we're going to do is X is going to go through W1, but X is also going to add to A. And then similarly, we're going to have 2 more additions here. So this is going to go here and up to here. And then this is going to go here and up to here. There we go. So let's write out the math just like we did before. So A is equal to W1 times X, because we're still doing this weight times X, but it's also going to be plus X. Right? Because we have this additional path here. So it's going to be A is W1 times X plus X. And we can obviously rewrite this a little bit simpler, and this will be helpful later. It's just W1 plus 1, right? Just take an X common, so you're just left with W1 plus 1. Similarly, B is going to be equal to W2. So it's going to be this W2 times A, right? A goes to W2, but it's also going to be plus A once again. So W2A plus A, which is again going to equal to A times W2 plus 1. And lastly, C is again the same thing, W3 times B, because we're going to multiply B by W3, and we're going to add B back to it. So this is, again, we can write as W3, or 3, plus 1. So that's our setup. And again, the loss will be just 1/2 C minus C bar, where C bar is our true answer, squared. So there we go. That's our setup. We can actually, though we won't really be using this, I think it's just good to see, we're going to go ahead and rewrite all of this out. We're going to use these forms here rather than these. We're going to need this side later. When we do the derivatives, we're just going to stick to this right now. So we can rewrite C is equal to, well, W3B plus B. And we know B is W2A plus A. So this is going to be W3B, which is W2A plus A, plus B, which is again W2A plus A. And again, we can plug in for A W1X plus X. So this is going to be W3. Let's do square bracket here. It'll be W2. A is W1X plus X plus A is again W1X plus X plus W2. Again, A is W1X plus X plus, again, A W1X plus X. Now, this is a annoying looking function, and we don't want to deal with it. So we'll be just dealing with, our chain form here and write everything in terms of A, B, and C. Otherwise, this just becomes an annoying derivative to do. So let's go ahead and redo the derivatives that we had done earlier, but let's kind of see what the relationships are between having a residual connection and not having a residual connection. So I'm just going to go ahead and erase this because we're not going to actually use it for anything. I think it's just good to see once the effect of what that looks like, but I just want to have space for what I want to do. So again, just like before, DL, DW3, right? Nothing crazy. So just like before, we can rewrite this as DL, DC, DC, DW3. Actually, no. Actually, yeah. No, that's correct. That's correct. Yeah. So DLDC, DC, DW3. Great. Well, we already know what DLDC is. We did that derivative before. It'll just be C minus C hat again. So it's going to be C minus C hat. There we go. And then DC dW3. So what we have here is C is W3B plus B. And let's erase this. Well, the derivative of C with respect to W3 should just be B, because this B is a constant, right? This is like saying y is equal to 2x plus 2. So dy dx is equal to 2, right? Just this 2. We don't care about this 2 at all because it's just a constant. So it just becomes a B. Huh. Well, this looks a lot like our DL dW3 from earlier, doesn't it? Right? DL dW3 was C minus C bar times B. So it looks like the residual connection doesn't have an effect yet. Okay, so that's our first setup. Let's do the next one. So we're going to do DL dW2. As you'll notice, the derivatives for a chain rule actually is exactly the same thing. This will end up being DL dW2. We again have to get to W2, we have to go through B. So we need DL dC, DC dB, dB dW2. So let's go ahead and do that. So we have DL dC, DC dB, and then we have dB dW2. So just like before, we know what DLDC is now. That's C minus C hat. we know dc/db, so derivative of c with respect to b, and this is why we wrote it in this form, because dc/db is now not just w3, but w3 plus 1. So we can write here w3 plus 1. Lastly, we have db dw2, so db dw2 is just a. Just like that. And let's just reorganize this just a little bit. So we write it kind of like what we had before. So let's leave the c minus c bar intact. So what we're going to do is just distribute on the w3 plus 1. So this will end up being c minus c bar times w3a plus, so that's basically w3 times c minus c bar and a, plus the 1, which will just leave us with c minus c bar times a. Well, does this look a little familiar? What you see up here, remember, is our original derivative without the residual connection was c minus c bar, w3 times a. That's what we had. So we see that resurface again. C minus c bar, w3 times a, is here. But we have this new derivative here. And how we interpret this, we'll look at in just a bit. But we have this new term here, and this term is actually our solution of why residual connections work. And we'll come back to exactly what that means graphically in a bit. But for now, what I want to do is just box this. So this we had before. This we had before. And the new thing is this. This is the new one. So this is brand new. Let's go ahead and do dl/dw1 again. So again, we need to do dl/dw1. And just like before, that's going to be dl, dc, dc, db. Now we need to go from db to da, and then dA to dw1. And we know what most of these values are. dl dc is again c minus c bar. dc db, just like we saw earlier, dc db is just w3 plus 1. So there we go. We have a w3 plus 1. We then have db da, which again is just w2 plus 1 because we took it common. So now we have an extra w2 plus 1 here. And then we have a dA dw1, and dA w1 is just x, right? So we have x here. And again, we're going to go ahead and distribute this center term out and then distribute it all out. So we're going to say this is equal to c minus c bar. This is going to be w3 times w2, so w3, w2, plus, we can then write this as, let's say, w2 plus w3 plus 1. Right, if we FOIL this out, you'll have w3 times w2, you'll have w3, you'll have a w2, and then 1 times 1 is 1. And the x, of course, at the end. So let's go ahead and multiply all of this out. So we're going to set, again, leave c minus c bar alone. We'll have a w3, w2, and then, of course, the x, plus, again, c minus c bar. We'll have a w2, x, plus c minus c bar. We have a w3, x, and then finally we just have a 1, so it's just c minus c bar times x. C minus c bar, x. So this is our derivative of dl dw1. So again, let's take a look at what was our original derivative before. It looks like it was c minus c bar, w3, w2, x. Well, don't we have one of these in our new derivative? And indeed we do. That is this chunk right here. That is our new derivative. Or sorry, that's our existing derivative. And we do have some new ones. We have 3 new terms. We have 1, 2, and 3. These are our new derivatives that appeared due to our residual connections. And now it's just time to interpret these. Like, what are we exactly dealing with? So let's just start with this one right here. So this one's the same as before, dl dw3, nothing changed there. For DLDW2, let's kind of think about this practically. We have basically to update W2, there's two directions our derivative can come from. We can either go straight through, which includes W3, or we can circumvent, which doesn't include W3. And do we see that? Let's take a quick look. We have one term that has a W3, and we have one term that doesn't have a W3. So notice that we have a W3, don't have a W3. So that means, and let's go ahead and delete these so it's clear. That means this one is the one that skipped over W3 entirely, right? We skipped over W3, and this is that extra gradient information that can flow backwards and not be affected by W3. So we just get more of that gradient information flowing backwards, as opposed to earlier where we didn't have that extra gradient information, right? We don't have another pathway for that gradient to flow through. And so again, this is super important. So let's interpret the next one. So again, this first term, C minus C, so this is DL dW1. So we have to go all the way back, right? Our gradient option number one is we just go all the way through, right? So our options are the first one, C minus C bar, W3, W2x. So that means to get to W1, we have to go through W3 and W2. So that's our regular gradient path. But as we know from looking, if we have too many of these derivatives going on, then you're just going to end up having a bunch of this, like stacking our chains together and then having gradient overflows and underflows. So what do the other ones look like? So let's erase that one for now. What do the other ones look like? This one here is C minus C bar W2x. So we don't see a W3 in here. So this one is skipping W. This one's skipping W3. So what does that look like? So if we're skipping W3, that means this path is going to be, it's going to go here, circumvent W3, and then go straight through W2. That's the pathway for this specific gradient information, circumventing W3. Okay, good. Let's look at the next one. This one seems to be skipping W2. So this is skipping W2. Okay, so let's see what that looks like. So this one is going through W3 and then circumventing W2 and then continue on. So this one's skipping W2. Okay, so that's the last one. And this last one seems to be skipping W3 and W2, right? We're basically skipping both of them. In this case, our gradient information is basically going forward, skipping one thing, skipping another thing, and then going back, completely circumventing W3 and W2. So do you see how this gradient information, basically we're accumulating all the different pathways. And when we actually implement AutoGrad in a future video, so we'll have a video and it's already in my Git repo, you can take a look, but we'll be implementing a completely working case of AutoGrad. You'll see this in a little bit more specificity, but you're seeing how we're just accumulating. To update W1, we're accumulating the gradients of all the ways to get to W1. So to get to W1, we either go through all the layers, or we go around one of them, or we go around the other one, or we go around both of them, right? Those are all the pathways to get to W1. But that's how this gradient information is flowing really nicely to W1 without being obstructed by W2 and W3, adding more of those additional chains in our chain rule operation. And that's basically it. That's the entire foundation or foundational idea behind ResNet and what allows us to train neural networks so efficiently especially super deep neural networks, without dealing with some of these issues. And you can just think to things like language models. If you've heard of GPT or BERT, which are models we'll be looking at later, they have very big models, like very deep models with complex architectures with a lot of things going on inside. And the only reason that works is because there's a lot of residual connections built in, so the gradient can flow between the model. And yeah, that basically concludes the the simple derivation. This isn't too complicated. Again, a very, very simple. I obviously skipped like biases, and these W's are not matrices of weights or anything like that, but the intuition is identical regardless of how you write it. This is just the easiest way I think I could explain it. So let's go ahead and take a look at the ResNet figure. Right? So by the end of this video, what we will have is a full ResNet implemented, but two variants, one with the residual connections, one without the residual connections, and you'll get to see how residual connections actually enable neural networks to train. So we'll get there very soon. But what I want to show you here is a 34-layer convolutional neural network. So like we saw last time in AlexNet, you should have already understood convolutions. You should know everything you need to know about convolutions. If you don't know about convolutions, then please go back to the previous video and just go in order. But assuming you know convolutions, this is just a regular convolutional neural network, right? 34 layers of a convolutional neural network. And most evidence shows that if you want to train a model this deep, you actually can't due to backpropagation. The intuition that I can kind of provide here is we know that neural networks are kind of hierarchical learning machines. It's probably the best way to think about it, right? Like early layers in the neural network are focused on learning the structure, like the low level information about your data, like edges and simple shapes, color information, things like that, things that are kind of specific about things like some of this low level information that we need to pick up. The later parts of the model, like these higher level features of the model, are the ones that's actually specific to your data set. Like if we're doing cats versus dogs, it can be the eyes or the ears or things like that. And we've kind of took a look at this in one of the earlier videos where we talk about the hierarchical learning patterns of neural networks. The problem is if backpropagation fails to update these earlier weights, that means these early features for grabbing from the data, right? These early features like lines and edges and curves and things like that are basically garbage, right? If we can't update these weights, then those early features that later parts of the neural network actually depend on to learn, they won't exist. They won't work. Right? There's nothing there. There's nothing that the model's picking up on because these weights, again, they're randomly initialized. And if by the time we get to, by backpropagation, by the time we do our chain rule to the beginning, if our gradient is basically 0 because of underflow, which is the most typical problem, if your gradient is basically 0, then these will remain randomly initialized weights. We won't have the gradient information to update them. And so the ResNet paper says, well, instead of just having a bunch of convolutions stacked on top of each other, and again, notice how many more layers there are compared to the VGG model, another one of the early neural networks. Notice how they provide these additional pathways for our gradient, which means at the beginning, right, just like we saw in our kind of easy example of the math of the gradient, to pass gradient to the beginning, we're going to have the gradient that flows all the way through the model, which will basically just be 0. But then we'll also have the ones that maybe go through all of these paths, right? It's just another way of gradients to flow. And we'll accumulate basically every combination. Like we'll have going through the entire convolutional neural network, or doing one skip connection going through all of it, or doing 2 of these skip connections and going through all of it, or 3 of them, or all of them, and just add them all together, and that'll be your effective gradient information that flows to the back. And so this is, again, a great way of allowing gradients to flow through your model. Today we'll be implementing specific, and again, this is the figure we saw before, right? We basically passed through some weight layers. We obviously did not include some ReLU or any activation functions in our example. Another difference between the example we did and the implementation is we had a residual connection after every single weight layer. Here in this picture, they have it after every 2 weight layers. In the implementation, it's going to be after every 3 weight layers. But regardless, that's the main idea. We basically have some skip connections over kind of chunks of the model is the best way to think about it. So this figure is probably all we're going to be looking at now. We'll be implementing the 50, 101, and 152 layer ResNets. We could also do these, but these are less interesting because we're looking to do a deep, like an actually deep neural network. So I want to walk through a little bit about what this figure is about. Like all the information we need basically to implement this model is in this figure. And there's a couple of exceptions. And I talk about that somewhere, I think after. Yeah, I talk about some exceptions, some problems, some things we need to think about that I haven't really talked about yet. So we'll look at that, and then we'll draw it out, we'll implement it, and we should be good to go. So let me just close that. There we go. All right, so ignore 18 and 34, but the principle is obviously identical. Every ResNet model will begin with a 7x7, a convolution with 7x7 kernels, 64 output channels. So these numbers you're seeing 64, 64, 256, yada, yada, yada. These are the output channels of that convolution. So we have 64 output channels. And in the beginning, we're going to have a stride of 2. And then we're going to do another max pool here with another stride of 2. And I believe the input size to these images are either 224. I think it's 224. So that's fine. And so these two are saying we're going to have a convolution and then a max pool. And we're good there. After that, what we have is a couple of different patterns. So let's just look at the 50 layer right now, because as you can see, most of it's the same. And then we'll talk about what everything else is. So these are called, this is basically a convolution block, or a block of 3 convolutions. These first 2 numbers here are the kernel size. So this is a 1x1 kernel. And we'll talk about what 1x1 kernels are, because we haven't really discussed that. And then you have a 3x3 kernel, and then another 1x1 kernel. And the first convolution will output 64 channels, the second convolution will output 64 channels, and the third one will output 256 channels. And this block of 3 convolutions, before the block we have an input, and then after the block we have an output, and then we do the residual connection between there. And we repeat this whole process 3 times, so that's for this one here. And then we update the channels, or upsample the channels. So now we can see we have 128 to 512, and we repeat this block 4 times. Then we repeat this block 6 times, and then we repeat this block 3 times. And notice the only thing that changes between these convolutions is the number of times we repeat the block. So it's 3463, or 34233, or 38363, but it doesn't really matter. The only thing that changes is the number of repetitions of every block. Another thing I want to point out, and this is important to keep in mind, and we'll dig into this a little bit more when we draw out the implementation so you actually understand the code, because I always find this implementation super finicky and annoying, but I think it's good to just do it once so you have it. We first notice that the first convolution, so the input here, the output of this first convolution will have 64 channels. The first convolution in the first block of 3 will have 64 channels, which means the output is 64, or the input is 64, and the output is 64. And then we're going to upsample from 64 to 256. So that's a 4 times output, right? We're going to multiply by 4. And then we're going to go from 128 to 512, which is again times 4. 256 to 1024, again times 4. And then 512 to 2048, so again times 4. So we're always going to have a 4-time update in the channels. And so what I want to do now is talk about 2 of the exceptions that we have to deal with, and why we have to deal with them. So remember, for residual connections, right? So what we have is a, let's just pretend we have some batch by channels by height by width, right? This is the typical shape we have for data. And this is going to go through some convolution, right? And let's call this height 1 and height and weight, height 1 and width 1 and channels 1, right? So whatever. And so convolutions, when you do a convolution, it can change the channel. So let's call this C2 times, and we know that some downsampling can happen as well, height 2 and width 2. Right, so we have a little bit of a problem, right? And actually, whoops, let me fix this here. we have a problem because now we want to take x and add it to here. So we have something that's batch by channels by height by width, all one. And then we have another tensor that's batch by channels 2 by height 2 by width 2. And these channels and heights and widths are not necessarily the same, which means we actually cannot add these together. We can't add together tensors that are of different shapes. That's like saying I want to take this vector here that has 3 numbers in it, and then take this vector here that has 4 numbers in it, and add them together. That obviously does not make sense. You can't add together vectors with different lengths, and you cannot add together tensors of different sizes, right? That's basically the main idea. So we have to do a little bit of work and figure out how we fix this. And so we're going to go through the 2 exceptions now, and hopefully that clears it up. And once we do, then the code will start to make a lot of sense. So let's go ahead and look at the 2 exceptions, and then look at the implementation details, and then we'll go ahead and implement it. So there's 2 opportunities for something to go wrong. Let's do the first one. So we notice here the block is a 1x1, so it's a 1x1 kernel. Again, we haven't talked about what 1x1 kernels are, but we'll see that in a bit. But we have a kernel of 1x1 with 64 input, and then we see that we have an input with 64 channels, right? We have 64 channels is the output of this first convolution. So our data x, right, will be some batch by 64 channels, by some height, by some width. We don't really care what the height and width are just yet. So we have that. And this is going to go into a stack of 3 convolutions. The first one is a 1x1 with 64 channels output, which means it'll have 64 and 64 out, and we'll see that in more detail a little bit later. The second one is going to be a 3x3 convolution with 64, and then we're going to have a 1x1 with 256 channels, which means the output of this convolution, and this is assuming we're going to do convolutions in a specific way such that the height and width don't change, and we can make sure they don't change by just changing our padding a little bit, right? We can just add some padding and make sure the height and width always stay the same. So in this case, if we have height and width, we're going to output a batch by 256 by the same height by the same width, right? We'll ensure that the height and width here is the same as the height and width here. If we go to add these 2 things together, we have a bit of a problem, right? Because this first thing has 64 channels, and the second thing has 256 channels. So these are tensors of different shape, so we can't actually add them together. And so in this case, we actually need a helper convolution, right? We need a helper convolution to make this work out. So we can take x, so we obviously can't add these together. We can take x is going in here, that's fine. We can create another convolution, so we can make sure this is a convolution that's a 1x1 by 256. So this will take 256 or 64 in and upsample it to 256 channels. This will provide a new tensor of batch by 256 by height. Again, we'll ensure the height and width don't change in this when we do this convolution. So this height and width, this height and width, and this height and width are all the same. But this 64 is now upsampled to 256. And now we can actually add these together, right? Because we have batch by 256 by height and width, and batch by 256 in height and width. So we're good to go, right? We're going to produce another batch by 256 by height by width. And that'll be it. Now you may be asking, well, Priyam, the whole point of the residual connection was to avoid convolutions, right? We want a nice flow of gradients through our additions so that gradient can just skip around these 3 convolutions. What's the point if we just add this other convolution here? Well, let's go on to the next block and you'll see what happens. So remember, we repeat this entire operation 3 times, right? So we first pass data into these 3 convolutions, and then we have an output, and then we want to add the input to the output, but because the input and output are of different shapes, we have to have this helper convolution here to upsample this 64 to 256 so we can actually add them together. Why don't we go ahead and do the second one? So this is our first convolution. Sorry, it's cutting through the page. We're again going to do another 1 by 1, 64. It's exactly the same, 3 by 3, 64, and then 1 by 1, 256. Okay, so this is going to take, this is 64 output. So we have 256 in, 64 out, which means at the end of this, right, we're still going to end up with a batch by 256 by height by width. Because remember, again, this height and width and this height and width are identical to each other. Now, because these two things are the same shape, we can go ahead and add them together. And that's basically it, right? So only in this first of three, only in the first block of the 3 blocks that we need to do here, do we have an exception. The other blocks are totally fine. And that's why in this implementation, actually, you'll see some of these like dotted ones. These dotted ones are basically, I think, where those exceptions are happening. So that's basically it. The first of the 3 will have an exception, but the other 2 will work out just fine. So that's exception number 1, right? We have a problem in the number of channels. Let's now do exception number 2. If you read down here carefully, downsampling is performed by conv 3.1, 4.1, and 5.1 with the stride of 2. So in this convolution here, in these convolutions here, the stride was always 1. And because the stride was 1, the height and width, this height and width is always the same. It never changed. But now they're saying in this next set here, in this one right here, and future blocks, right? In these blocks, the first set of 4, there's 4 of them. So in the first one of the 4, there's going to be a downsampling with a stride of 2. So it's going to be a stride of 2. So that means if we pass in a tensor with some height and width, the output will be height over 2 and width over 2. Because like we saw before, having a stride of 2 basically halves the spatial output or the spatial resolution by 2 in both dimensions. So let's go ahead and draw that out and see what that looks like. So the final output of this tensor, right, these 3 will have 256 channels, and it'll be some height and width because no spatial downsampling happens here, only kind of messing with the channels. So we're going to have some batch by 256 by some height by some width. And then we're going to pass this into a block, and this block is 128 and 512, so it's going to be 1 by 1, 128, and then 3 by 3, 128, and then 1 by 1, 512, because it's always going to be times 4. But this is also going to have a stride of 2, right? A stride of 2. So when this goes in, what's going to come out is a batch by 512. So batch by 512. So we went from 256 to 512 by height over 2 by width over 2. Because of the stride of 2, we have halved the height and the width. So again, when we do this residual connection here, we can't just directly add them together, right? That's the problem, because in this case, both the channels and the height and width are different. But we know how they're different, right? We know the pattern. So what we have to do is, again, create a convolution, that an extra convolution that's going to be 1 by 1. It's going to have a 512 output, because we need to make sure this 256 channels is upsampled to 512, so we have more channels, so they add together. And we're going to make sure this has a stride of 2, right? A stride of 2, which means when we perform this convolution, we'll end up with a batch by 512 by height over 2 by width over 2. Which means now these two things are free to add together, giving us a batch by 512 by height over 2 by width over 2. And let's write that H a little bit better. Height over 2 by width over 2. So that's our setup. Now, what about the next convolution? So again, we're going to repeat this entire process, right? We're going to do a 1 by 1, 128, 3 by 3, 128, and 1 by 1, 512. right? We're going to again do another set of convolutions. In this convolution, the stride is now 1, right? So remember again, it said that downsampling is performed by conv1, for1, and 5-1. So only the first set of 4, the first set of 6, and the first set of 3 will actually have downsampling. The other, so in the first one we'll have a downsample by 2 or a stride of 2, but on all the other ones we're going to have a stride of 1. So because we have a stride of 1, this will stay the same. This is going to be batch by 512 by, again, this will be height over 2 by width over 2. We're not going to downsample it a second time, in which case these two things are free to be added together, right? Regular residual connections. So the exception I'm saying here basically is the first set of each of these kind of blocks will have an error. We need to make sure we do an extra convolution just to make sure the shapes match up. But every other one are basically fine. There's no problem there, and we just rinse and repeat. We'll just write a for loop basically to do that. Let's talk about the last thing, and this is how we plan on implementing this. Basically, we need to keep track of a couple small things. So notice how this, when the first tensor, right, we're going to pass in a, actually, let's start here. We're going to have a variable in our implementation. And I'm drawing this out because this is always the part that confuses me the most. We're going to have a variable called planes. I'm using the word planes here. It's actually channels, but I'm trying to keep the implementation basically identical to the one you see in the PyTorch hub or in Hugging Face or something like that, just so you're looking at industry standard code rather than just code I wrote for convenience. So I'm trying to keep it as similar to that as possible. But we're going to have to provide something called planes. And the planes are going to be 64, 128, 256, and 512. Now, where did these numbers come from? Well, that's our 64, 128, 256, 512. That's what it is. And each of these, 64, 128, 256, 512, will be upsampled. 64 will go to 256, 128 will go to 512, 256 will go to 1024, and 512 will go to 2048. Yes. So 64 is going to go to 256. 128 is going to go to 512. 256 is going to go to 1024. And 512 is going to go to 2048. Right? That's our, and notice these are all times 4. So in the default implementation, we'll always have a upsample planes by 4. Always by 4. And that's what you see here. So let's go ahead and see a little bit of what this algorithm looks like so you understand how we're using the variables in the implementation. And again, this is just to give you a general idea. And then when we implement it, we'll again come back and reference what I drew out here. So first step, right? We're going to create a variable called inPlanes. And we're going to set it to 64 because we know that's our starting point, right? That's 64 here. And then we're going to have another variable called planes. And we're going to start with 64. Obviously, we have 64, 128, 256, 512. We're going to have 4 different ones. But for now, we're going to start with 64. So that's going to be 64 and 64. And let's look at the first definition. So right now, we're not going to think about these kernel sizes. We're just going to think about our channels. So our first convolution will output 64 channels, which means the first block of 3 convolutions here, the first one has to take in 64 channels, right? The first input is 64 channels. So what we're going to have here is 64 in the first convolution. And as provided, all of these numbers right here are the output channels, right? The number of outputs. So it's going to, the first convolution is going to be 64 in, 64 out. And then the next one, if we have 64 output, again, we have 64 output here. So that means if the first convolution outputs 64, the second one has to take in 64. And then again, it's set to take 64 out. Again, if the second convolution outputs 64, the third one has to take in 64. But they tell us that they want 256 as the output of the third convolution, or times 4. So 256 out. There we go. So this is our input-output number of channels, or planes, in our first 3 convolutions, the very first 3 convolutions. And this is going to be conv2 underscore 1. So this is conv2 underscore 1. Now, where did these numbers come from? So let's kind of see what we did. We have this in planes here, 64. In planes keeps track of how many inputs do I have to a block. And this 64 is this 64 right here. Then we have planes, which keeps track of how many channels do I have inside basically all of my models. So 64, 64, 64, 64. That's this 64 right here. And then finally, we have this 256 here, which will be planes times 4, which is going to be, in this case, 64. So it's going to be 64 times 4. And this is planes, not in planes, but just regular planes. 64 times 4, which is 256. And that's how we get these numbers. Okay, so we've done conv2 underscore 1. Let's go on to the next one. So one thing to keep in mind here is we inputted something with 64 channels. This is going to output something with this whole block, right? At the end of this block, we're going to output something with 256 channels. So the next convolution set has to take, if we output 256, the next one has to take 256 in. But just like before, notice it's 64, 64, 256. So we need to output 64 on the first one, output 64 on the second one, and then output 256 on the third one. So it's going to be 256 in, but then we're going to output 64 here. If we output 64 on the first one, then we're going to have to take in 64 on the next one, and then output 64 on the second one, as described. And then again, if we output 64 on the second one, we're going to have to take in 64 on the third one, and then output 256, again, as described, 256, in the third one. So where do these numbers come from? And this is the critical part about how we do the implementation. We are now, after the first block is done, which is typically the exception block where we have to deal with stuff. After the first block is done, we're going to update. So we're going to create in planes. Instead of in planes being this 64, we're going to do in planes is equal to planes times 4. So that's going to be this planes right here times 4, which is 256, which makes sense because this output here, this final output of the previous block was plane times 4. So the new in planes also has to be planes times 4, right? That's just what it has to be. So this 256 is now what informs what this input should be. Again, this 64 here is going to be this 64, this 64, this 64, this 64. And again, this 256 here is going to be planes times 4 for the same reason we had that earlier, right? This planes times 4. So same reasoning. And like we saw, we actually repeat this whole process 3 times, right? We have a third one. So let's just go ahead and do the third one. The third one should be identical, right? We have, remember, so this will now output 256. So we're going to have 256. And then we're going to have 64, 64, 64, 64, again, 256, right? It's going to be identical to the previous one. Well, this 256 here already informs this, right? We already know this should be 256 because of this one here. And then this 64 here is informed, right? It's this 64 again, informs all of this. And then this 256 is once again planes times 4. Again, 256. So are you understanding how this is kind of working? We're basically doing we set our in planes as 64 for the first block. We complete the first block using the rest of the information we have. The first block is going to output planes times 4, which means the in planes for all the next blocks is going to be 256, which is plane times 4. So we just update in planes to be planes times 4. That gives us our 256, and everything else stays the same. And that's basically the setup. Let's go ahead and do the next one, right? So we have 3 blocks with 64 planes. Now we're going to have 4 blocks with 128 planes. We're not going to do all 4 of them. We're just going to do a couple. And that should kind of set up the pattern that we're looking for. So now, again, remember, in planes is still 256, right? That's the variable we have, 256. And we're still going to need that, so we're going to leave that alone. But planes is now going to be 128, right, for the next couple blocks. So let's go ahead and do this. So the final convolution of the previous block, this block here, is going to output 256, which means this is going to take 256 input. And again, we know this is 256 input because, let's make this a little bit smaller, because the in planes over here is still 256. So that's going to go right here. That's how we know. And we set everything else. So we see the first block outputs 128, second block outputs 128, third block outputs 512. Okay, so this is going to go from 256 to 128, right? First block outputs 128. If the first thing outputs 128, then the next thing has to take in 128, and we know this outputs 128 again. Terrible 8s, sorry. There we go. And then if this outputs 128, then again we have to output 128. And then this is going to be 512. So again, where do these numbers come from? This 128 is where all these 128s came from. And this 512 is where it's just planes times 4, which is now going to be 128, this 128 times 4, which is 512. Okay, so that's our first chunk. Now for the next one, right? We need to update to the next level. So this block will output something with 512 channels. So that means the next thing has to take in 512 channels. And how do we know to do this? Because remember, the first block is basically our exception case where we handle stuff. All the next blocks, all the blocks that come after it, are all the same. So just like we did before, right? We had some in planes here and we used that for 64. But then before we did all the next blocks, we just updated in planes to be planes times 4. Because if this is 256, which was planes times 4, then all the inputs to the next things will be 256. That's the pattern. So just like before, we finished our first block. So now it's time to update in planes. So now in planes is going to be planes times 4, right? So that's going to be 128 times 4, which is 512. And this 512 is what informs this right here. Planes is still 128. So remember, we're going to go from 512 down to 128, 128, 128, 128, and then 512. And this is again going to output something with 512 channels, which means for the next chunk, right, we're going to again repeat this. We're going to have 512 input, which we already know because the in planes tells us that. That's our 512. And then again, we're going to do 128, 128, 128, 128, and 512. And again, these 512s here are going to be planes times 4. And again, planes times 4. And when I say planes, again, I'm talking about this planes right here, 128. So are you kind of seeing the pattern? There's basically two things going on. We have something called planes, which we provide, and then in planes, which we just update once after the first block. And this is effectively the implementation. So let's just start putting this together piece by piece, and hopefully it'll make sense as we reference back to some of these figures that I drew. Let's go ahead and do this. We're again going to reference this very closely this tells us everything we need to know to actually implement this model. So that's how we'll be doing it. So let's go ahead and do our imports real quick. So we need torch. We need torch.nn as nn. Import torch.optim as optim. From torch vision, import transforms. From torch.utils.data, we need the data loader. We need from torch vision.datasets import image folder. We're going to need that just for training, doing the cats versus dogs dataset again. From tqdm.notebook import tqdm. And then we need import numpy as np and import matplotlib.pyplot as plt. And then just to hide any annoying warnings, we're going to do warnings.filter warnings ignore. The other reason we're doing ResNet 50 specifically is one of the last videos we'll be doing in this kind of sequence of introductory tutorials will be actually reproducing the ResNet 50 paper, or the ResNet paper. We won't be doing any reproducing today. Today's just to teach you how to build the ResNet, but in the future video, we'll learn, how do we take ResNet, train it on multiple GPUs, get a learning rate scheduler in there, that sort of stuff, and that'll all make sense once we get there, and reproduce it on the ImageNet dataset, right? Using multiple GPUs, that sort of stuff. So that's why I think it's really important we actually talk about this, because this is actually pretty crucial for what we're attempting to do. So let's go ahead and set it up. So again, a little bit of cheating here. I went ahead and printed out the cases where we have a problem. So see how X is 2 by 256 by 64 by 64. So that's the input to the block of convolutions. But the output is 2 by 60, or actually, I got it backwards. The input was 2 by 64 by 64 by 64. The output is 2 by 256 by 64 by 64. So these are not two things we can add together. So this is a case where the spatial dimension, 64 by 64, is the same, but the number of channels is different. So we can't actually add together tensors that have different shapes, right? The other three cases is where both the channels are wrong, right? So we can see 256 to 512, 512 to 1024, yada, yada, yada. But the image space is also wrong, right? So notice how it's 64 by 64 here, but the X is 32 by 32. So we can't add those things together either. And so we just need to handle a lot of this stuff. Before we kind of continue going, though, I do want to explain a little bit about what a 1-by-1 convolution is. So let's do rand equals torch.rand. And let's do a batch size by, let's do, 16 channels. And let's do a 32 by 32 picture. And let's do a convolution is going to be nn.con2d. We're going to take in 16 channels. We're going to output, let's say, 256 channels, and our kernel size is 1. So you can do con rand. And actually, that's not helpful. We need to see the shape. So let's go here, dot shape, and there we go. A 1-by-1 convolution allows us to change the number of channels without affecting the image space at all. And that's basically the idea, right? We have remember we started with the 16, it upsampled it to a 256 with a kernel size of 1. And this is just an easy way of changing the number of channels. And how does this actually work out in practice? Well, it's exactly what you think. It's probably good to just draw this out real quick. Let's say we have a, so this should feel familiar because we drew a lot of this convolution stuff in the previous video, but let's pretend we have a 2-by-2 image, 2-by-2, and we have A, B, C, D, right? That's our image, and this is a 1-by-2-by-2. Let's say there's just one channel, right? Or actually, we can make it more interesting. We can say there's 3 channels. Let's do 3 channels just to make it a little bit more interesting. 3 channels. So there's 3 here. And let's say we, let's draw this here as well. There we go. if we do a 1-by-1 convolution, right? So that means our filter is 1-by-1, but because there's 3 channels, we have 3 things here. So we have 3 weights, right? 3 weights or 3 parameters. And so let's say this is A1, A2, A3 for the 3 channels, right? This RGB. So that'll be basically me taking, here are my weights, weight 1, weight 2, weight 3. And I'll be doing basically W1A, W1A1 plus W2A2 plus W3A3. And this will provide some, this will be some number. Let's call it Q, right? Let's call it Q. And let's call it Q1 because it'll make 1 channel, right? So this is filter 1, right? This is filter 1 right here. Well, let's say we have a second filter, filter 2. And actually, more importantly, before we go on to the second filter, we're going to have to repeat this process, right, for A, B, C, and D. So we're again going to do W1, B1 plus W2, B2 plus W3, B3. And let's get Q, R. Then we'll have W1, C1 plus W2, C2 plus W3, C3. And this QR, let's call it S. And then we'll have W4, C1, or not C, but D1 plus W2, D2 plus W3, D3. And let's call this T, QRST. So those are outputs. And because this is filter 1, let's call this Q1, R1, S1, and T1. So this convolution, all we did is a weighted average of the pixels. Like that's basically all we did, a weighted average of an individual pixel across the channels, right? So this will produce, this filter 1 will produce a Q1, R1, S1, T1. Just like that. And that's just the first filter, right? We're going to have another filter, let's say filter 2, right? So that'll be, let's call this weight 1, 1, 1, 2, 1, 3 for for the filter 1. This will be weight 2, 1, weight 2, 2, weight 2, 3. And this will produce something, again, very similar, but, it'll be a different set of Qs. It'll be Q2, R2, S2, T2. And just like before, we're going to repeat this K times, right? K times up to filter K, which will be W1K, W2K, W3K, our 3 filter weights. And it'll produce a, just like before, QK, RK, SK, TK. And we stack all these things together, right? We stack all of this together. And it produces a filter, set of outputs, just like this, where you'll have QI, RI, SI, TI, where I is basically in K, right? We have K different outputs. And that's basically the idea. A 1-by-1 convolution allows us to easily upsample the channels by just doing a weighted average of the pixels, right? So basically, for one weight, we're basically just doing W1 times the entire first channel plus W2 times the entire second channel plus W3 times the entire third channel, add all the channels together, and you get QRST, or Q1, R1, S1, T1. And we can repeat that for all the different filters, however many we want, and that will provide us the number of channels we want. Again, there's other ways to do this. We could have also done a kernel that's not 1-by-1 and just ensured we had enough padding to provide the same image space, but this is just an easy way of doing it. So there's a bunch of ways of doing it. Our main goal is basically we want to change the number of channels without changing the image resolution. So if it's a 2-by-2, we want to keep it 2-by-2, but just change the number of channels. And there's a bunch of ways of doing this, but again, this is the most common. So we can go here. So we can do a kernel size of 1, for example. If we do a kernel size of 3, notice how the image gets slightly smaller, So that's not helpful. We got the right channels, right? We got the right number of channels, but the image gets slightly smaller. We can also provide padding equals same here. And this will basically compute ahead of time what the padding should be for us to ensure we get the same output, right? The same size output. And both of these are valid solutions. It's just in the way that they implement it in the ResNet model, they're using the 1x1 kernel as the trick. But again, I don't think it would actually make a difference if you changed it. If we also do padding equals 1, notice it's actually the same. And I believe this is basically the trick we're going to be using to ensure the size doesn't change. We're going to always be using a padding of 1 because with a kernel size of 3 and a padding of 1, with I believe like these even numbers, it doesn't seem to ever change. We can try 30 and 30, for example. Okay, I stand corrected. Oh, wait, 30, 30. Yeah, so kernel size 3, padding 1 seems to always just give you the, and it actually makes sense. If you draw it out, it's pretty clear, but it always gives you the correct option. So those are your options. We can either use a kernel size of 1 and not care about padding, or we can use a kernel size of 3 and we can have the same padding. But our main goal is to make sure that we just change the number of channels, which happens in either case, but keep the image resolution identical. And as long as we meet that condition, then this should work regardless. We're just going to follow the way the ResNet paper does it. Again, it shouldn't make a difference. So the implementation of ResNet actually has two parts. We're going to define the block. So let's go here. It's up here. We're going to define a block, basically a residual, one of these blocks. And we're going to ensure that this block basically can be called over and over again to just dynamically create. Because I personally, if there's 50 layers in a neural network, I do not want to write out all 50 layers individually, like conv1, conv2, conv3, yada, yada, yada. So to avoid it, we're going to express one of the blocks, like, define it, and then just call a function that can just create it for us. So we're going to first create this block. We're going to call it the residual block. So class residual block, nn.module, def init, self, and we're going to have, and again, I'm using planes, but really it's channels. I'm just trying to follow the implementation you'll see online, just so, so I'm actually teaching something helpful and you don't have to like refigure out what they're doing again. So this should be really close to what they're doing online. We have in planes, downsample equals none, middle conv stride equals 1, and residual equals true. Okay, so what are all these? We already know what in planes and planes are. In planes identifies what is the number of input planes to expect for this residual block specifically, and planes is basically the number we care about, the 64, 64, 128, 128, 256, 256, 512, 512, where we talked about how planes were basically this, right? The number of planes. Which one is it? And the final channels will always be planes times 4, right? That's the important part. So that's what this is. In planes and planes we've talked about. Downsample is the it is the extra convolution we may need. So by default, it's set to none because in most situations we won't need it. But in case our identity doesn't add the output, so if the input to the block doesn't match the output to the block, then we need to provide a downsample to ensure those shapes match up. So we're going to have this as none, and then we'll pass it in when needed. The middle conv stride, so this is just the stride, like we saw before. The first set, so if there's 4 of them here, the first one of the 4 of these blocks will have a stride of 2. Everything else has a stride of 1. So by default, I've set it to a stride of 1, but the first block will always have a stride of 2 in these last 3. So not in this first conv 2x, but only in these last 3. Also, it doesn't really matter which one of these 3 convolutions. I don't think it does. I don't think it would matter which one of these 3 convolutions you do that stride of 2 on, but from the implementation, they did the stride of 2 on the middle one. So that's why I called it middle conv strive. So middle conv strive. And then this is something I just added in. This is residual, whether or not we actually want to do the residual connection or not. And this is how we're going to test, do residuals actually matter when training these models. Like, what is the effect of the residuals? So we're just leaving that there, and we'll toggle it on and off in the future, but that wouldn't be a part of the actual implementation you see from PyTorch. So super.init. So we've done this. I guess this is also something else we haven't mentioned. PyTorch models are very modular. Like, you can write blocks and methods and things like that, and then create one model that actually puts it all together. We're going to be doing this more and more as we start writing more complex models. So this is a very simple example where we're going to create something called a residual block. And then when we define the ResNet, we're going to be calling this residual block over and over again. But as long as we write all the methods the same way as a class with a def and a forward, then it all kind of works out. So you'll kind of see how that works as well. So let's go ahead and do it. So we know that there's 3 convolutions in each of these. So we're going to do self.conv1 is nn.conv2d. And we know the input to the convolution will always be in planes, and the output will always be planes. And we know from the provided implementation, the kernel size is always 1 for the first one, and the stride is always 1 for the first one. And again, going back here, let's see here. Here we go. Right, the input to the convolution is to our residual block is always in planes, and everything else is planes, and the final thing will be planes times 4. Right, that's how we're doing it. So so how we define it is always there's in planes, and then planes, which will be everything else, and then the final convolution will be planes times 4 is the output. So you have self.conv1, self.conv2 is nn.conv2d. This is going to be planes to planes. This is going to have a kernel size of 3 as defined. The stride will be the middle con stride, right? So in most cases it's 1, but sometimes it may be 2, right? For those 3 convolutional blocks that we have. So we have that as 1, but we just need to pass that in as a variable. And then we have padding equals 1. So we already talked about this, doing kernel size 3, padding 1. We could have also done padding is same here, right? Actually, that's not true at all. We need this as padding is 1, because if we do padding is same, then when we have a stride of 2, it won't actually downsample. It'll just pad it to give the same resolution. So we're just doing this. This is how it's defined, so that's how we're doing it. And this will ensure that we basically get a half downsampling of our image. Okay, next we have our third convolution. Self.conv3 is again nn.conv2d. We're going to have planes. And now we're going to output planes times 4, right? We're going to output 4 channels with a kernel size equals 1 and stride equals 1, just like before. And that basically sets up all of our convolutions. Now, again, something to keep in mind, we are doing a 2D ResNet meant for images and things like that. You could also do a 3D ResNet meant for videos or point cloud data. And really all you'd have to change is from 2D to 3D. And this should work just fine. Similarly, you can do a 1D ResNet for audio and things like that. And then you just change this to conv 1D, right? So it's very flexible in that way. So we have our convolution. Now, we've talked about this before. Typically, when we do convolutions, we want some type of normalization happening. Actually, in neural networks, and typically we want some type of normalization happening. We talked about how batch norm is one of the most effective ways of doing this, but you could also use layer norm or group norm or some of these other methods. But for now, we're going to be using batch norm, right? We're going to use batch norm. So we need a couple of these batch norms. So we need self.batchnorm1 is nn.batch norm 2D, and this is going to take in planes, because if this first convolution outputs planes, then the second one, or the batch norm, must expect to have planes number of channels to expect. And then we have self.batchnorm2 is again nn.batchnorm2d. Again, it'll be planes because the previous convolution outputs this many channels, so we just need to expect to get that many channels. And then finally, the third batch norm, self.batchnorm3 is nn.batchnorm2d. And now this should be planes times 4. because if the previous thing outputs planes times 4, then this must also expect planes times 4. And this should basically be our setup for the entire model, right? So we have planes, in planes, which tells us the number of input planes to a block, like we saw. Then we have our planes, which will be 64 for everything. And then we have the output will be 64 times 4, or planes times 4. So there we go. We also need to keep track of a couple other things in our class definitions. So we can do self.relu. So we're going to be using the relu activation, nn.relu. So we're just going to call that once and just store that. So we have this activation function. We also need to store our downsample and residual, just in case. So we're going self.downsample equals downsample. And this will just be a layer. It'll just be another convolutional layer, which will pass outside of this block, right? So we'll provide it if needed. Otherwise, it's just none, right, if it's not there. And we also have our self.residual equals residual. This is, do we actually want to do the residual connection or not? This is, again, just to see, do residual connections matter when training neural networks? Great. So now that we had this, we could have actually packaged this a little bit better into a sequence, but that's fine. We're going to keep it simple. Forward, self, x, we're passing in our data. So step 1 is, remember, we have, and let's go back here. We have x. We pass x through some data, and then add x to, or sorry, you pass x through some layers or some of the neural network, and then we add x to the output. So what we're going to do is before we pass x through all these layers, let's just store a copy of x on the side for later. So we're going to do identity equals x. We're just going to go ahead and just store that on the side, and we're going to use it a little bit later. And now we're going to do exactly what you think. We're just going to pass our model through all of these layers. So we're going to do self.conv1 x equals self.batchnorm1 x is self.relu x. So we've passed it through the first 3 layers. Then we have x equals self.conv2 x equals self.batchnorm2 x, and then x is self.relu x. So that's our second set. And then third one, x is self.conv3x, x is self.batchnorm3x, and then x is self.relu x. So that is our third set. So this is me passing my data through my 3 blocks of convolutions, along with some batchnorm and activations in between them, right? So that's my single block happening right here with in planes, 64s for our planes, and then 256, or planes times 4. Now that we got that, now whether or not we want to do the residual connection depends on this. Obviously, we do want to do it. This is, again, just a test. Do they matter or not? So we're going to do if self.residual. So, do residuals matter? We'll find out. Step 1 is if our identity, like in the cases that we saw here, right? When the identity does not match the output, we will have passed in something for downsample. So we're going to do if downsample sample is not none, right? If it's not none, then we're going to say identity is equal to downsample, or self.downsample identity, right? So we, again, let's go back here. If x batch by 64 by height width does not match batch by 256 by height width, which it won't in that very first block because the input is 64 but the output has 256 channels, or in one of the future ones where we pass in something with 256 channels but there's also a stride of 2, so both the channels and the height and width, so notice how the channels and the height and width don't match, we need to use an extra convolution, right? An extra convolution to get the shapes to match up so we can actually add them together. That's the big idea. And this extra convolution is what we're calling downsample. So we'll be passing that in here, which we're storing right here. And this will just be an extra convolution. And you'll see how we define that convolution a little bit in the future. But for now, we just have a downsample, right? And this will ensure that identity and x have the same shape. Once that's done, we can do x is equal to x plus identity. right? We're just going to add them together, and we can return x. So again, just to verify, we will only do this identity stuff if we want a residual connection. And then if we pass in something to reshape identity so it actually matches x, then this downsample will happen. And then otherwise, if downsample is not there, then they're already the same shape. So we don't really have to care about it. And we can just go on to adding x to identity and we're good to go. We return x. Otherwise, if none of this happens, then we just return this x up here with none of the residual connections added. And this is effectively our residual block. Nothing too crazy. I'm pretty sure this is right, so we'll find out if there's a bug later on. So there we go. Now we're going to write a class ResNet and n.module. Right, so we're going to actually define our ResNet now. And in the init, we're going to provide self layer counts. So layer counts is going to tell us, so we know that there's 4 blocks, for example, 1, 2, 3, 4. It's going to be 4 sets of blocks, but layer counts will tell us how many of each block we want. So in the case of a ResNet 50, for example, it'll be 3, 4, 6, 3, right? It'll just be a list with those 3 numbers. And we'll kind of see what that looks like in a bit, but this will just be a list of 4 numbers, basically. We have num channels. This is the number of channels to expect in your input. So we'll be working with RGB images, right? So we're going to be starting with 3 channels. And then num classes, right? This is how many things we're going to be predicting at the end. In our case, it's just going to be 2 because it's dogs and cats. But if you're doing ImageNet, then it'd be 1,000, so on and so forth. And then we're going to do residual equals true, which we need to pass in, right? But that's how we'll tell the model how many residuals we want. And just to start testing this, we can do def ResNet 50, right? We're going to residual equals true, num channels equals 3, and num classes equals 2. We're going to return a ResNet with all that information, basically residuals equals, or residual equals residual, num channels equals num channels, and a num classes equals num classes. And we also need to tell it how many is the layer count. So we're going to do layer counts is equal to, as per the paper, 3, 4, 6, 3. There we go. So that'll return back our ResNet in a easy way, or ResNet 50 in an easy way. And so if we run ResNet 50, we should get a problem. All right. Has no attribute module. Oh, right. We actually haven't done anything yet here. So super.init. There we go. So we're ResNet. It's an empty model right now because we haven't done anything yet, but we're about to fill it in. Good. So let's go ahead and just store some of this stuff. So we're going to do self.residual equals residual. Store that as a class variable. Self.num channels equals num channels. Self.num classes equals num classes, and self.layer counts equals layer counts. Just so these variables are available to us in the object in the future if we're curious about looking at them. So we have that. Now for the important part. We're going to set self.inPlanes as 64. That is our starting point because we know that the first input to this block will have 64 channels. So we're going to just go ahead and store that. And we'll update self.inPlanes as needed as we kind of build out the model. For now, it's going to be 64. We also note that before we have these blocks, we actually have a convolution and a max pool, and also a batch norm, of course, happening here. So this convolution is going to be a 7x7 convolution. It's going to take 3 input channels in our case and output 64 channels with a stride of 2. And so that's basically what we need to make sure we do. Also, if you look at the implementation online, they use a padding of 3. I'm sure that was just to get it to this 112 size that we're looking for. So I'm just going to throw a padding of 3 in there. This is mostly just to get shapes and stuff to match, right? So there's not much there's not much like logic that goes into it other than just trying and seeing what works. So we're going to do, this is our initial set of convolutions. Or I guess convolution. It's just one. We're going to do self.conv1 is nn.con2d. It's going to have 3 input channels, so num channels. And the number of output channels is going to be self.inplanes, right? As we saw, we expect to output 64 channels with the first one, and then everything else will basically just be based on that. So self.inplanes. We then use a kernel size equals 7, a stride of 2, and a padding equals 3, just because that's how they had it implemented. I don't think it would actually matter what we use there, but that's fine. And then we're going to do self.batchNorm1, again, is nn.batchNorm2d. And this batch norm is going to take self.inplanes, right? Because if the previous convolution outputs in planes number of channels, then our batch norm expects in planes number of channels. And we'll have an activation, self.relu equals nn.relu. And then we'll have a, as explained in the figure, after this first set of convolutions, we have a singular max pooling happening as well, a 3x3 max pool with a stride of 2. So we can go ahead and do that as well. Self.maxPool is nn.maxPool2d. It's going to have a kernel size of 3, a stride of 2, and a padding of 1. And again, I got the padding of 1 because that is what they had in the that's what they had in the implementation, and I'm sure they just tried it and got it to the shape that they wanted. So we're going to keep it like that. So we got our initial set of convolutions. Now it's time to define the rest of the model. Now, the whole reason we made the residual block earlier is just so we can write a function that will just automatically generate the model for us. So we don't actually have to manually write every single block out, because that'd just be annoying. So that's what we're going to do. So we're going to do self.layers1 is going to be self.makeLayers. And we're going to have to write this method here, makeLayers. We haven't written it yet. Where we're going to provide it layer counts 0. So what is the number of planes to expect in this, not planes, the number of blocks, the number of repetitions of the blocks that we want. So that's the 3, 4, 6, 3. So how many times do we want the first block? That'll be these. So that'll be, we have to provide it that. We also have to provide it the planes. So we can do planes equals 64 for the first one. Stride equals 1 in the very first one, right? So we know the very first, all the convolutions in the first set of layers will just have a stride of 1. And we'll deal with the ones with stride of 2 in the future. So we have to write a method called makeLayers. We're going to give it self, a num residual blocks, planes, and stride. And again, the stride only applies to the first layer, and we'll see that in a bit. So by default, our downsample is none, right? By default, downsample is none. And layers is going to be nn.moduleList. So I don't think we've actually seen module list yet, but it's just a regular list. It's just a regular list, but it's a special PyTorch list. It's a PyTorch list that just lets us store modules in it. It could be simple modules like convolutions, linear layers, recurrent neural, whatever you want. It can be simple modules, or it can be more complex modules like something that we wrote, right? An nn.module. This residual block is a module, so we can store it inside the module list. And it's just an easy way to pack things together and organize them. You could obviously also not use them. What you don't want to do is use a regular list, because it may not play well with like moving to the GPU and organizing and saving the model. When we go to save the model in the future, it may not play well with that. So we're just going to use a module list. It works exactly like a regular list. It appends, concats, you can pop, it doesn't matter, but regular list, just a PyTorch list, that's all. So we have two conditions. We know that if stride does not equal to 1, that means we did a downsample, or we're doing a downsample, so it does not equal to 1. Or if self.inplanes does not equal to planes times 4. And let's just check that real quick, right? So two conditions. Condition 1, if our stride is not 1, so in this case 2 is basically the other one, stride of 2, we know the resolution of the output of the block will be half the resolution of the input of the block, the spatial resolution, height and width. So if that happens, we need a convolution to do this identity mapping, right? That's important. The other one is if our self.inPlanes does not equal to planes times 4. So if our input planes right now is 64, as it is, but in planes is 64, but planes times 4 is 256, as it will be at the end of this block, then that 64 input and the 256 output don't match. And so we have a problem, right? That's not going to work out. And that's again right here. If the input is 64, but the output is 256, we won't be able to add these tensors together because they have different number of channels. So this condition will not be met, right? So, or will be, this condition will be met where the in planes of 64 does not equal to, well, 60. Our planes at the beginning will be 64, so 64 times 4, 256. They won't match. We will update the planes in the future, in the next step. That'll make it 256. In this case, so for the next block, when we create remember, we're going to have to create 3 of these blocks in the next block. In planes will be 256, and planes is 64. So 64 times 4 is 256. So then 256 and 256 match, and this condition will no longer be met, but we still may have a problem with the stride. So these are our two conditions, right? If our stride is not 1, our resolution will not be the same. And if the input number of planes to the block does not match the expected output to the block, then the tensors won't be, summable because they're different shapes. So these are two conditions, and we just have to keep these in mind. If these are the case, then downsample will no longer say none. We're going to make it a nn.conv2d. It's going to be a self.inPlanes. I did in_planes. So it's going to take input planes. So if it's not planes times 4, then we need to make sure it's planes times 4. So we're going to do planes times 4. So it's going to take in planes because that's what the block is getting. And it's going to output what the block will be outputting. So 256. Again, just to recap, just so it's super clear, this block is taking in 64 and it's going to be outputting 256, which means the tensor going in has 64, but the tensor coming out has 256, which means we need to take the tensor that's going in, pass it through another convolution to take it from 64, which is our in planes, to 256, which will be our planes times 4. And that's what this is, right? Self.inPlanes, 2 planes times 4, to ensure that they're the same, because we know this block will be outputting planes times 4. Now that we have that, we need to deal with the stride as well. And all we have to do here is just say kernel size is 1, because we want to ensure that the spatial resolution doesn't change if the stride is 1. But then we set the stride equal to stride, right? So with a kernel size of 1 and a stride of 1, if this is 1, right? If this stride is 1, with a kernel size of 1 and a stride of 1, the image space resolution will be the same, but we'll change the number of channels. And that's exactly what we need for this first block. Because remember, in the first set of convolutions here, we aren't changing the image space by doing a strided convolution. In the next block, we need to change both the channels and the image resolution, in which case this will be a stride of 2. So something with a kernel size of 1, but a stride of 2 will provide an image that's exactly half the size. So we just need this. Now, every convolution should typically be followed up with a batch normalization. So instead of downsample just being a convolution, we're going to stack it with a batch norm. So we're going to do nn.sequential, just so it's a single module that we can call, but it's just going to be 2 different things. It's going to be, the second will be nn.batchnorm2d, and this should be planes times 4. And hopefully that made sense. This is probably one of the more confusing parts that took me a little bit of time to wrap my head around. If you're still a little bit confused, I would recommend just kind of dissecting it and going through the code and just printing stuff out to see how things are lining up. But this should give you a general idea, batch norm 2D, of what's going on. Again, if the stride is not 1, the image is being downsampled, which means the input is twice as large as the output. So we need to downsample it here. That stride is stride. So we'll set it to 2. If the in planes don't match the output, then we need to make sure that our input actually matches the output in the number of channels. And then once this downsample here, this self.downsample is applied to the identity, then this identity is now the same shape as x. So, or this x right here. So this x and this identity will be the same, and I'd actually be able to add them together. Without this, it'll throw an error saying, hey, we have things that can't be added together, and we'll see an example of that in a bit. I'll force the error so you can see it. So there we go. We have our downsample done. Now we know that, remember, there's going to be 3 blocks in the first one. So let's do the first one manually, which has these extra kind of conditions. And if you'll notice, actually the first of every single one of these blocks is the one with the problem, the thing that causes us to have these exceptions we need to handle. All the other blocks are just rinse and repeat. Nothing is happening. So we can just go ahead and manually define the first one and then just for loop to make the other one. So we can do layers.append. And again, layers is a module list. This is why we can just append a module to it. We can do ResidualBlock. And this residual block will take an inPlanes equals self.inPlanes. It'll have planes is going to be equal to the number of planes in this specific block. In this case, it's 64. So inPlanes is 64, and then this is 64. And then we will provide it a downsample equals downsample. So this is one of the few cases where we actually have the downsample. This first layer will always, as I mentioned, the first block is always the one with the exception, always the one with the problem. So basically this first one in the stack of these layers will always be the one with the downsample. So there we go. And then we're going to have a middle conv stride is equal to the stride of what we have here. Again, this stride will be 1 in most cases except 2. So again, the first of each of these sets of blocks is the one that will have a stride of 2. So this is where we pass it in. So this is the first of the set of layers when we repeat. So this is the one that could have a stride of 2 if we pass this in as 2. And then we'll have a residual equals self.residual. And that's just us saying, do we want a residual connection or not? And that's for testing in the future. So there we go. That sets up our, looks like there's a small error. I believe this has to be, let's see, middle conv stride. Is it breaking on the, yeah, it is breaking on that. I probably spelt it wrong. Middle conv stride. No, let's see here. Oh, I messed it up here. So we have, there we go, spelt it wrong. There we go. So notice our first layers. The first layers of the ResNet is, actually, let's just keep going. These are those initial layers, right here, the very beginning part. But let's do the rest of this. So we have layers. Now what we need to do is just do the rest of our layers. So like we saw, we had 64 as our in planes set by default, and that was okay for the first block. But now that we're outputting 256, the in planes to every other block in this set of blocks will have 256. So we have to go ahead and update self.inPlanes to be planes times 4, and then just rinse and repeat. So we can do self.inPlanes is going to be planes times 4. We're going to go ahead and update that. And then we can do for blank in range num residual blocks minus 1. The reason we're doing minus 1 is because we've already created one of the layers here. We just need to make the remaining layers below. So it's just minus 1 because we only have to do the remaining ones. We'll do layers.append. Again, residual block in planes is equal to self.in planes. So notice here, this in planes was the 64 from up here. This in planes is the updated 64 times 4, 256. And again, this is 256 because this residual block, the first one, will output a 64 times 4, 256. So we need to make sure it's the same. A little bit weird. It takes a little bit of time to wrap your head around. Just, again, go through the code in a little bit more detail and just spend some time printing some stuff out, and it should click pretty easily. So now we have in planes is self.in planes. Again, planes is just planes, right? Because regardless of what in planes is, in this case 256, we're still going to go down to 64 because that was the number of planes for this specific set of layers, 64. So it's going to go down to 64, stay at 64, and then output 256 again at the end of the block. So this will just ensure that we're going from 256 down to 64, and then this is going to do 64, 64, 64, and then we're going to output again 64 times 4 at the end of our convolutions, just like that. So we have planes equals planes. We then need a downsample equals downsample. Actually, no. In these, downsample is always none because we had dealt with the downsample in the earlier layer, and downsample is just none by default, so we can ignore that. And then residual equals self.residual. There we go. If we print out the layers that we just made, print layers, you can see we just produced all of these layers here. So what we can do then is just return layers. Now, if we just return layers on their own, that would be fine. But this would mean that because it is a module list, to pass our data through a module list, we actually have to for loop through the list, just passing in, one layer at a time, and that's fine. We can make our life easier. Instead of for looping through the list, we can just create a sequential. So when we forward pass through it, it'll internally for loop through it. It's still a for loop, but PyTorch just does it for us, so we don't have to worry about it as much. Sequential, and we'll just unpack it's actually just one star. We'll unpack the layers into here. It doesn't do anything. It just cleans up the code a little bit more so we don't have to for loop through something. And there we go. So let's take a look. What we have is our initial convolution. So it's convolution bash norm relu max pool. You see that right here, convolution bash norm relu max pool. We then have, so notice again, this first set of convolutions will output 64 channels as expected. And then the first block of convolutions will go take in 64, output 64, and then take in 64, output 64, take in 64, output 256. The problem is the input here was 64, right? The input to this block was 64, but the output has 256, which means we need to use this extra downsample to take our 64 and then upsample it to 256, throw it through a batch norm because that's just good practice, and then we will end up we can then perform that identity sum. We can actually add it together. In the other ones, though, just notice it's just 3 convolutions. But now that our output is 256 of the previous block, the next block expects 256. And we go 256, 64, 64, 64, 64, 256. And we output 256. And in this case, we're golden because if the input had 256 channels, and the output is 256 channels, and we never changed anything about the actual image resolution, then we can add them together. We don't need this extra downsample. We don't need to kind of manage that and write an exception for that. And this is, again, notice how this is just identical to this, because every block afterwards ends up being identical. If I had 10 of them, then the first one would still be this, and then I'd have 9 more of these. But I just have 3, so we have 1 here, and then 2 of these. That's it. It's really as simple as that. So now we can go ahead and and actually one other thing to note is notice how really convenient PyTorch is. So I called this layers 1. So that's why they called it layers 1 here. And layers 1 is a sequential. It's a sequential of residual blocks, right? So it's a sequential of residual blocks. And then each residual block has convolution batch norm, yada, yada, yada. But inside a residual block, I have another sequential called downsample. And then inside this downsample, I have these things. So it really nicely keeps the names for you, indents things for you, things like that. So very convenient, very nice. Lets us avoid, makes it very easy to read what our model looks like. And this comes in handy later. Okay, good. So that's our first set of layers. But we don't just have one set of layers, right? We have 4 of them. 1, 2, 3, 4. Now, this should basically be a copy paste. So we can do that. Let's rename these. This will be layers 2, layers 3, layers 4. This is going to be layer counts, but it'll be 1, 2, 3, because it's, how many of each do we have? It goes in the pattern 3, 4, 6, 3. So we have, 3, 4, 6, 3. The planes. So how many planes do we have? In the first one, it was 64. The second one, it was 128. The third one is 256. And the fourth one, it's 512. So it's just that. It's going to be 64, 128, 256, 512. And whatever we pass in, 64 planes, it'll upscale to 4 by 4, because it's always by 4, because that's how we set it up, planes times 4. And the other important thing is on these last 3 layers, so on layers 2, 3, and 4, we'll have a stride of 2. And again, this stride of 2 only applies on the very first block. So this middle con stride will be 2. Otherwise, it'll use the default middle con stride of 1 of what we set up here, right? So this is, again, the first of the 4 and the first of these 6 and the first of these 3 will have a downsample of 2. And everything else will just have a regular no downsample, so stride of 1. Similarly, the first of these 4, the first of these 23, and the first of these 3 will have a downsample of 2. But then, again, you'll have no downsample, or just a stride of 1 for the remaining ones. And that's the main part. So these 3 will have a stride of 2. And that's what does our image downsampling. Lastly, we need a average pool. In this case, we just average pool. So you'll end up with some batch by channels, by height, by width. And we'll have to flatten this, right, to a batch by channels times height times width. Right? That's our final thing. Now we know our final output channels here will be, I believe, 512. The final output when we add it together, or was it 20? What was it? Actually, yeah, it'll be 2048. So the final channels, right? The final output of the final block will have 2048 channels. So we know C right here will be 2048. And the height and width will be something, but in this implementation, they just go ahead and use an adaptive average pooling and just average everything up. So we average across, and it should be a pretty small image space. If we take a look here, actually they provide it. It looks like it is a 7 by 7 in the image space, but 2048 channels. So we basically average up across the channels, and maybe a good way to express this is a drawing. So we have, let's see, where did I put here we go. So what we have is a 7 by 7 image space, but we have kind of 2048 channels. And so what we're going to do is just average up every channel independently. So basically the average of this 7 by 7. So the average of these 49 numbers, and then the average of the next one. So we'll have 1 channel, 2 channel, 3 channel, dot, dot, dot. Each of these are 7 by 7, 7 by 7, right? And we'll just average these up to be a number. So it'll be 1 number, 1 number, 1 number, dot, dot, dot. And then we just concatenate all those numbers together into a vector of length 20, 48. Right, so nothing crazy. So we're just averaging up across the image space. Do we need to do that? No, we could have also just flattened it into a 2848 times 7 times 7, but it seems to not affect too much about what we're doing here, so we're just going to stick to the implementation. Right, so this will be, let's see, self.averagePool is equal to nn.adaptiveAveragePool 1, 1, right? So we're going to average down all the way, and then self.fc, the fully connected layer, is going to be nn.linear. There's going to be, again, 2048. It's going to be a 2048 length vector. So after doing the average pooling, so we started with a batch by channel, or 2048, by height, by width, right? That's our shape. Let's space this out. That's what we have. And then after the average pooling, we'll end up with a batch by 2048 by 1, and 1s are just unnecessary extra dimensions, so we can really just get rid of them. And it's just a batch by 2048, which means our linear layer will expect 2048 inputs and num classes outputs, right? However many classes we expect. What are we predicting? One difference to note here is in our AlexNet implementation before, we actually had a couple of linear layers stacked together. Like we went from like 512 to 4096, and then there's another one from 4096 to 4096, and then another one from like 4096 to the number of classes we have. Most neural networks I see today just have a single prediction head, like just one linear layer that does the prediction. If there's more, will it be better? Maybe, maybe not. I'm not entirely sure, but that seems to be the gold standard. You basically have a super complex encoder like convolutions or transformers or whatever, and you'll have a single layer for your predictive task at the end. And it seems to work out pretty well. So that's what we're going to go with. There we go. So 2048 or 512 times 4. And this should, looks like it's actually average pool 2D, not just average pool. There we go. And here's our full model, right? So we have our initial layers. We have our first set of layers, which is going to be 3 blocks. Notice how the error correction on the identities in this first block. Then layers 2 has 0, 1, 2, 3. So there's 4 blocks here, which makes sense. Notice again, the error correction is on the first block. We then have layers 3, which has 0 through 5. So there's 6 blocks here. Again, the identity correction is happening on this first block. And then we have our final block here, which just has 3, identity correction on the first block. And then we have our adaptive pooling and our linear predictor. And that's it. This is the entire ResNet implementation. It's a little bit finicky. Again, I would recommend go through it, print stuff out. Just take a look for yourself because you don't really understand it until you try to do it yourself. But I hope this explanation with some of these drawings were helpful in kind of what's happening in the image space, the channel space, and then how these in-planes and planes work together, because that's what really confused me the first time I attempted this implementation. Okay, so now that we have this, now is really the moment of truth to make sure it works. So let me double check real quick. What is the image size we plan on using? I think it was, yep, 224 by 224. So we're going to say this is the model. And, oh, actually, we forgot a complete part of the model. We've only defined the layers. We have not defined how we pass data through those layers, right? So we still need to write a forward function. So let's do that real quick. So this part should be easy. Def forward self x. Okay, So our first set, x is equal to self.conv1x, x is equal to self.batchnorm 1x, x is self., there's a relu x, and x is self.maxpool x. So there we go. So that's our first set of these convolutions, right? Again, referring to the figure, that takes care of these two things right here. And now we just pass our data through all the layers. Now, just to express again why we did nn.sequential layers here, so unpack the layers, is if we didn't, then we'd have to do for layer in self.layers layer 1. Let me double check that's what I called it. Layers 1, so layers 1. We'd have to do x is equal to layer x, which is a completely fine way of doing it, but we'd have to do that for layers 1 and then do it again for layers 2, layers 3, layers 4. It's a little bit messy in the code. By doing a sequential, we can again just do x is equal to self.layers 1 x, and just it'll just do the for loop for us internally, so it's not a big deal. And we're gonna have to repeat this 4 times. Oh, there we go. We're going to pass it through 2, pass it through 3, pass it through 4, and there we go. And let's just print out, and this is the important part, x.shape at the end of this. Okay, so we're going to create some random data. Rand is torch.rand, batch size of 4, 3 input channels, and each channel is 224 by 224. So model rand, looks like we have a bug. Downsample is not defined. Okay, because I called this, if self.downsample, right? And there we go. As expected, right? We expected let's go up, a 7x7 output here. And that's exactly what we got. A model with 2048 channels and a 7x7 output. So it looks like this is exactly the implementation as expected in the ResNet paper. So that's exciting. Well, we have to go ahead and wrap it up then. So we have to do x is equal to self.averagePool, what did I call it? Average pool, just average pool. Yeah, average pool. X, print x.shape. So there we go. But we have these extra dimensions that we don't need, just extra ones. So in PyTorch, a quick function is squeeze. So squeeze, if you have extra dimensions, so ones are basically just extra dimensions, right? They don't mean anything. They're just kind of filler dimensions for our tensors. .squeeze will just automatically remove them for you. So anything that's a 1 dimension just gets removed. That's all. There's also an unsqueeze, and I'll be using that later to kind of add extra dimensions, but in this case we don't need them. So it's 4, 2048. And then we do x is go to self.fc, our head, and then again we can print x.shape, and there we go, 4x2. And that's basically our model. Again, if this was ImageNet, we would just make this 1000, but same idea. We're just doing 2 because we're doing cats versus dogs today. So this is evidence, right? This means our model's working. We can actually return x here. Return x here. This is kind of our model, completely functional. And let's just quickly make sure this works. Residual equals false. So yeah, still works without the residual connections. If we take a look at our model, so let's see here. So we do have downsamples actually, to make this the most correct. Actually, no. This is fine. Well, I don't know. We actually don't really care about these this extra self.downsample if we're not actually adding anything to it. So I bet if I just added an extra thing here, if so let's do if self.residual, right? If we're doing residuals, then if these other conditions are met, yeah, it looks like it works. And so it just removes some of those. Granted, those layers never would have actually been used because we never actually passed gradients to them. But that's just a little bit cleaner, right? If we are not doing any residuals, then we'd have no need for those extra downsampling blocks and whatnot. So either way, this gives us a fully functional model ready to go. So we've defined the ResNet 50 here. Let's just go ahead and do the other ones real quick. They should be identical. Again, the reason we're not doing ResNet 18 and 34 is because there's only two convolutions per block, where the residual block that we wrote here has 3 convolutions per block. Not that you couldn't update it, you just have to rewrite the residual block for these, and I'm more interested in the deeper models anyway, so that's why we're doing this. So we have ResNet 50, we have a ResNet 101, and then we have a ResNet 152, I believe. And ResNet 101 is 34233. So 34233. And then ResNet 152 is 38363. So this will be 38363. There we go. Now, just another thing that we haven't really seen yet. Model is equal to ResNet 50. Let's just create it. And we have a model. Here we go. You might be curious, how many parameters does this model have? So we can do for name param in model.named parameters, print param break, right? So these are the parameters of one of the layer, the very first layer of the model. We can do param.numL, which tells us the number of elements inside a tensor. We can also do print param.shape. And this shape should seem pretty familiar to you. So we have, if you haven't seen this before, shapes of convolutions are always, this is 7 by 7 because our convolution here, where do we go? Yes, this one. This first one is 7. So the kernel size is 7 by 7. So our convolution is, the weights of the convolution is 7 by 7. We have 3 input channels and 64 output channels. And so that's how you're saying, remember how I mentioned that convolutions, what it is basically, if you have 3 channels, each are 7 by 7, then you have 7 times 7 times 3 learnable parameters. But convolutions are also a filter bank, right? In the way that they implement it. So we have 64 different convolutional filters, each filter being 3 by 7 by 7. That's just the way I like to think about it, right? So we have this. And so we can do num parameters is 0. And we can do num parameters plus equals param.numL. So this tells us that we have what? 1, 2, 3, 1, 2, 3, 1, 2. So we have about 23.5 million parameters in a ResNet 50. A ResNet 101 will have, let's say, 1, 2, 3, 1, 2, 3. So about 42.5 million parameters in a ResNet 101, and then a ResNet 152. So this has about 58.2 million parameters, right? So these are pretty large models, right? Pretty reasonably large models, but nothing crazy and compared to like our billion or trillion parameter models you see today in language models. So either way, this is basically the setup. Hopefully this made sense for the most part. Again, if you're stuck on something, please go through the code. It'll be helpful. There's some things we didn't include in here, but we could because it's good practice, like a dropout layer. So we can add a self.dropout is nn.dropout, and we can do 0.5 for our dropout probability, right? That's just good practice. I don't think there's a dropout in the original implementation, but maybe there is and I just forgot it. So we can add one of those in. X is self.dropout. Right, so we've added a dropout layer, and we obviously have batch normalization and everything else already in here. So I think we're good to go in this case. So let's go ahead and train our model. So this training script will be almost identical to the one we did earlier. So I'm going to copy paste a little bit of it. So this is just our data prep. Again, exactly the same as what we did for the AlexNet. So if you're a little bit confused, just look at the last video. But again, we just need to normalize our data because that's good practice. Resize to 224 by 224, some random augmentation. This is the easiest one, but I threw it in there just so we have it. The conversion to a tensor, and then a normalizer, right? To actually normalize our data just up here. And then we load our images, split our data into training and testing. So nothing crazy. This is exactly the same as before. And our training script will also be identical to before, but I'll do it again for anyone that's just watching for the first time and didn't see the previous ones. So we're going to do def train. We're going to pass in the model, the device, the number of epochs we want to train, the optimizer we want to use, the loss function we want to use, the batch size we're interested in using, the train loader, and val loader, right? So all the things we need to train our model. We're again doing a very simple training script today on dogs versus cats. We'll be writing a much more complicated distributed one using accelerate and stuff in the very end of this sequence of tutorials, so you can see how you'd reproduce something like ResNet 50. So our log training, it will be the same as before. Epoch, we're going to store the epoch. We're going to store the training loss, the training ACK, the validation loss, and the validation, lowercase v, validation ACK. Right, so there's our training, log training. Hopefully I can do this without any bugs, but we'll find out. So just like before, for epoch in range epochs, right? For every epoch, we're going to do print starting epoch epoch plus 1. It's just so we're starting from, like, if we're training for 10 epochs, it'll go from 1 to 10 rather than 0 to 9, like how range works. And then we're going to set the model into train. And I guess I'll explain that in just a second. So let's just get through this first. For image label in TQDM train loader, we're going to do image, make sure everything's on the device. Image label is equal to image.toDevice, whatever we're training on, GPU, CPU, hopefully a GPU. So we have that. And then we do optimizer.zero grad, zero out all the gradients. We can do out is equal to model, pass our images through it. We can then do loss is going to be, scroll down just a little bit, loss is going to be our loss function. It'll be cross entropy loss, but that's fine, between the output and the label. We then have our training losses, and yes, I forgot that. We need to store for every epoch the training losses. Training ACKs is going to be 2 empty lists, and then validation losses, validation ACKs, again, will be 2 empty lists. Just like that. We're going to do training losses dot append loss dot item. We're going to go ahead and store that. And then we also need to calculate the accuracy. So our predictions is going to be torch.argmax axis equals 1, right? We need to store what is our prediction, which is whichever the largest number is. So the argmax, that's the index. And then our accuracy is equal to predictions equal label, right? Where are we equal to each other? A dot sum, add up all the ones where they are equal, and then divide by len predictions, which will give us our accuracy, or percent of things we got correct, or where they're equal. And then we'll store our training accuracies dot append accuracy dot item. And there we go. So we can do loss.backward to update the model, and then optimizer.step to actually update the model. And there we go. Then we have to set the model into evaluation mode. And this is the thing I want to mention a little bit, because I don't know if I talked about this, or if I did, I might have just forgotten that I did, but this is really important. There's a reason we set the model into training and evaluation mode. So there's a couple changes that happen, but there's kind of a couple of really important ones. The first one is the dropout. So in dropout, for every forward pass we do, we will be randomly deleting 50% of the nodes, right, for this linear layer. And that's the intention of dropout. That's how we use it. But we only want to perform dropout during training. When we're evaluating the model, we actually want to use the entire model. We have no interest in dropping stuff out when we're actually using the model. And so model.train and model.eval toggles the dropout on and off. So during training, we will be using dropout, but during evaluation, dropout will be turned off. So we'll actually be using the entire model. The other thing that changes off in dropout is batch normalization. So again, if you remember, in batch normalization, we're passing batches of data to the model, and batch norm tries to estimate the mean and standard deviation of the data at that point in the model. Like after this convolution, what is the mean and standard deviation? And after this convolution, what's the mean and standard deviation? So we can effectively normalize our data. So it's computing mean and standard deviations here, and it does it based on a buffer that it has inside, and it just keeps a running statistic of what's happening. But we only want to update these statistics and compute the mean and standard deviation and kind of figure that out when we're training. When we are evaluating the model, we just want to use the running statistics that's already there, like whatever it's already computed. We don't need it to compute it again or update those numbers. And so again, model.eval will turn off the batch norm update steps, right? So batch norm will just become stagnant. It'll have some mean and standard deviation that it's already estimated during training, and it'll just go ahead and use that rather than trying to update it again. It has a couple other places it changes stuff, but those are the two main ones that we care about right now. So that's why we have a model.eval. Everything here can just be copied in because we're going to use all this anyway. But a couple changes. So first, val loader, right? We're going to be iterating through our validation data. There's no, when we evaluate our model, there is no zeroing gradients. There is no gradients. We're just evaluating. We're not updating the model. And we don't need to compute the computational graph when doing evaluation. So we can do with torch.no grad, or you can also use inference mode, right? Either one is fine. We'll use no grad for now. There we go. So with no gradients being calculated, we're going to pass images through our model. We'll compute the loss like normal, but instead of training losses here, we're going to just put it in the validation losses to store that there. Instead of the training accuracies, we're going to stick it in the validation accuracies, and there's no loss backward update, any of that. And now that we have that, again, just like last time, I'm just going to copy this because nothing's happening. I'm just being lazy. And so we have here, we're going to go ahead and just average up our training losses, accuracies, validation losses, accuracies. Go ahead and store that information inside our dictionary right here, and then just print it out so we can see what's happening. And so now what we're going to do is, looks like there's a bug. What could be wrong? Oh, comma. There we go. So now we're going to go ahead and train two models, one with residual connections, one without residual connections. So we're going to do device is equal to CUDA if torch.cuda.is available, else CPU. There we go. And we're going to print, just print out training on device. Just like that. Do training on CUDA. If you don't know, there's a quick command. You can do NVIDIA SMI, and it'll print out your like your CUDA resources, basically. So this is like my personal workstation, two A6000s. So it shows you right here. You can do the same in Google Colab, for example, and it'll show you like whatever GPU you have available to you on Colab. But yeah, that's fine. So that's just a quick trick to make sure everything's working. We're going to train for 10 epochs. We're going to use a loss function. It will be nn.cross entropy loss, and this will be the same for both models with and without residual connections. And we're going to use a batch size of just 128 for now to keep it simple. Train loader will be a data loader around our train data set with a batch size equals batch size. We obviously want to shuffle when training, and num workers equals, let's just say, I don't know, we can use more, 8. And then val loader is again a data loader with a val data set. Batch size equals batch size. We don't need to shuffle when validating, so we can turn that off. And again, num workers equals 8. And so we can do model equals ResNet. I don't know. Let's train the 101. Why not? And we'll do residual equals true. I spelled model wrong. Right, so that's our model. That's what we're going to be training. Nothing too crazy. And we need to make sure the model is equal to model.toDevice. Make sure it's on the GPU. Optimizer is equal to optim.atom. We're going to be a simple atom optimizer. Params equals model.parameters. Learning rate is 0. Let's just do that. You'll see later, actually, when we go to reproduce ResNet, they use, I believe, the just regular stochastic gradient descent optimizer with a learning rate scheduler of like a decay schedule, and we'll see that, a step decay. We'll see that later when we actually go to implement or reproduce the ResNet 50 paper with accelerated in the future. For now, we're going to keep it simple. We're going to print training with residuals. Right, and then we have ResNet with residual, and let's call it with residual model, right? Because we return the ResNet, not to ResNet with residual, and then with residual model. It's going to be train. We're going to do model equals model. Our device equals device. Epochs equals epochs. Optimizer equals optimizer. Loss function equals loss function. Batch size equals batch size. Train loader equals train loader. And val loader equals val loader. So that's our model. And once this model is done training, we can go ahead and do is equal to that dot to CPU. Right, so we're going to offload the model that's sitting, actually it should be this one, the second one's model. We're going to offload the model onto the CPU, so it just frees up some, frees up the memory. After that's done, we're just going to copy this, again training without residuals. And to do this, we're just going to copy paste. All of you are identical. So we're just going to stick you right there. And in this one, we're going to do without residual, without residual, without residual, without residual, and residuals equals false. But everything else is the same. And let's see what went wrong. 0D or 1D target tensor expected, multi-target not supported. Okay. I've never seen that error before, so let's just see what's going on. Let's print out out.shape, print label.shape. So, out.shape, label. Did I make a mistake somewhere? Why is the label? Oh, whoops. Haha, label. I was replacing, I just had, this is image, so that's not good. Okay, label, and then label. There we go. Any luck now? Any other bugs? All right, let's see what else there is. CUDA out of memory. Oh, it's probably because I just ran it 50 times. So let's do kernel restart and run all. Missing requirement argument. Oh, I made this mistake last time too. All right, so this should be, let's see, this should be out and out. Yeah. I don't like actually doing a lot of this deep learning stuff on Jupyter notebooks because Jupyter notebooks always hold on to the memory even when something doesn't work. It doesn't automatically just clear the memory, but that's okay. We're just doing this for learning. What else is wrong? Training accuracies is not defined. I must have just spelled something wrong. So let's do train. Oh, I called it training ax. So training ax. Let's make sure everything else is correct. So training ax, training losses, validation losses, and validation ax, which means your validation ax, and you are training ax. Sorry, it's always little bugs like this that get me. There we go. Now it's training. Okay, so we're gonna let this train, but we don't really care because with the magic of making videos, I've actually already trained this model. So I'm just gonna go to that and show you. So here you go. The model's training, no big deal. This is the important part I want to point out. So this is me plotting the cross entropy loss during training. Now, obviously you're noticing some overfitting happening here, but what we have is the red and green are the training losses with residual connections. And then the blues are training losses without residual connections. And notice how without the connections, basically nothing is learned. The loss stays stagnant. It's unable to update the model, most likely because the gradients are super small. It can't learn. And you could actually test this. I didn't do it here, but you could actually plot the gradient. So a good way to debug models actually is to plot the gradient kind of magnitude at the different layers. It's a good way to check like model health as it's training and debugging and things like that. And if you see like ridiculous gradients in a layer or no gradients in a layer, then you know you have dead neurons or something is exploding, and it's a good way to debug. But so you could do that, but this should basically tell you that without a residual connection, you don't got anything. There's nothing to, it can't learn. It's basically stuck. With residual connections, you can actually train and learn, which is exciting, right? So this is the importance of residual connections. They're going to show up all over the place for all sorts of stuff. As another example, if we look at, so this is something we'll implement a little bit later, but if we look at my like Roberta model, for example, and we look at the transformer, let's look at the transformer block. Here we go. Where are we looking at? Here we go. X is equal to x plus self.dropout. X equals x plus self.feed forward. So as you're seeing here, we have those residual connections. And these residual connections is what makes transformers even trainable with our current method of training, which is backpropagation. Right? So again, as a recap, this is fine. This can train. As a recap, what we talked about today is residual connections enable deep neural network training. The reason they enable deep neural network training is because it allows gradient information to flow through the model without being stuck at every step. Because when you multiply a bunch of numbers together for chain rule, if you multiply lots of small numbers together, you're going to get zero gradient and the model can't update. And if you could multiply lots of big numbers together, you're going to get basically an infinity, floating point overflow. And again, it just will be completely unstable. You'll get NaN losses, basically. It won't be able to update at all. And so because of these things, we need to use something like residual connection, again, to provide a different pathway for our residuals, our gradient, to flow through. And this derivation is basically that. How you see that instead of my derivative in this case, right, the straight through gradient, instead of my gradient just being c minus c bar w3 w2x, which is just me going straight through all these parameters to update w1, it instead becomes a sum of going straight through plus the combination of all the pathways there. So straight through, skipping both of them, skipping one of them, skipping the other one, and getting there. And that's kind of what this derivation should have shown you. And then the rest of this was just like the annoyances of implementing ResNet. I would never actually implement ResNet on my own. There's no need to. You can just grab ResNet. So when we do the future implementation to reproduce ResNet 50, I'm just going to grab the PyTorch ResNet 50 because there's no reason to do this. But this is identical to the implementation that we saw. So I hope this video is helpful. I do think it's important to at least do this once. And ResNets are still a very commonly used architecture as opposed to AlexNet, which is definitely not used today because they're not very deep models. And if you look at the ImageNet scores for ResNet versus AlexNet, it's a huge difference. And so that's why, again, ResNets are used still today. Either way, I hope this was helpful. If you have any questions, please just drop them down below in the comments. Now that we've done this, we are off to the races to sequence modeling. So we'll be now actually looking at recurrent neural networks. And once we've done that, we'll learn accelerate. And then we'll start implementing all the stuff that interests me: autoencoders, variational encoders, and transformers, and all the other fun stuff that I want to do. So either way, I will see you in the next video.